A linear graph is a line-shaped graph that can be written as y equals mx plus b. M is the slope. For every 1 unit you go to the right, you rise by m units. B represents the y-coordinate of the y-intercept, which is the point where the graph crosses the y-axis. This can be found by setting x equal to 0 in the equation y equals mx plus b, which gives y equals m times 0 plus b, or y equals b. Because the form y equals mx plus b directly gives the slope and the y-intercept of the graph, it is called slope-intercept form. A linear function is a special case of a polynomial function. It is a first-degree polynomial. It is also possible to write an equation for a linear graph given its slope m and a point that it passes through, x1, y1. We begin with the equation, y equals mx, which gives us a line of slope m passing through the origin. We can shift it vertically by y1 by replacing y with y minus y1. Y minus y1 equals mx. Then we can shift it horizontally by x1 by replacing x with x minus x1. Y minus y1 equals m times quantity x minus x1. Overall, shifting the line has the effect of moving the line to intersect the point x1, y1, where the point x1, y1 basically acts like the origin did. This form of the equation is known as point-slope form. The final common form is called standard form, which is ax plus by equals c, where a, b, and c are integers. This form separates out the variable terms from the constant term. However, note that some linear equations can't be rewritten in standard form, like y equals square root 2 times x. Linear equations are used to model variables with a constant rate of change. For example, the acceleration of a falling object is proportional to the time it has fallen, so the graph of a falling object's acceleration over time is a straight line. A quadratic graph comes from a second-degree polynomial function, y equals ax squared plus bx plus c. Every quadratic graph is a parabola, which is a roughly U-shaped curve. If a is positive, then the parabola opens upward. If a is negative, then the parabola opens downward. The greater the magnitude of a, the more sharply the parabola bends. The graph of a quadratic function can help you find the points where the function attains a value of 0, often simply called the zeros or roots of the function. Equivalently, these are the points where the graph intersects the x-axis. In general, for a quadratic function, there are 3 cases to consider. 2 x-axis intersections. The function has 2 real-valued zeros, each with multiplicity 1. This also means that the discriminant of the function, b squared minus 4ac, is positive. The discriminant is the value inside the square root in the quadratic formula x equals negative b plus or minus square root quantity b squared minus 4ac over 2a. 1 x-axis intersection. The function has 1 real-valued 0, which has a multiplicity of 2. This means the discriminant is equal to 0. No x-axis intersections. The function has no real-valued zeros. Its zeros exist only in the complex numbers. When this is true, the discriminant is negative. Quadratics have many uses in modeling phenomena in the real world. One of the simplest examples is parabolic motion. A projectile, an airborne object with no forces acting upon it except gravity, traces out the shape of a parabola as it flies through the air. A parabola is an example of a conic section, which is, roughly speaking, the intersection between an infinitely large cone and a plane slicing through it. The equation for the graph of a circle is quantity x minus h squared plus quantity y minus k squared equals r squared, where r is the radius and h, k is the center of the circle. This equation can be derived from the definition of the circle and the Pythagorean theorem. A circle is defined as the set of all points in a plane that are at an equal distance, the radius, from a given point, the center. For the simplest case, imagine a circle centered at the origin. Draw a radius line segment from the center of the circle to some point on the circle. This line segment's length is r. Now, say that the point on the circle has coordinates x, y. Draw a vertical line segment from that point to the x-axis. Then draw a line segment from the point you reached back to the origin. The three line segments form a right triangle. The lengths of its legs are x and y, and the length of its hypotenuse is r. Now we can just apply the Pythagorean theorem. X squared plus y squared equals r squared. So we know that this equation captures that particular point on the circle. But there's nothing special about the point we choose. We can do the exact same thing for all of the infinitely many points of the circle. Thus, x squared plus y squared equals r squared defines a circle of radius r centered at the origin. To generalize this so the circle can be anywhere in the plane, we must think about graph transformations. Replacing x with x minus h shifts the graph h units to the right within the plane. You could think of this as shifting the plane to the left while leaving the graph in place, meaning the graph moved relatively to the right as a result. Similarly, replacing y with y minus k shifts the graph k units upward. So, to center the circle at the point h, k, we just have to use the following equation. Quantity x minus h squared plus quantity y minus k squared equals r squared. One important case is the circle of radius 1 centered at the origin, given by x squared plus y squared equals 1. This circle is the basis of the trigonometric functions sine and cosine. If you start at the right of the circle and travel some distance theta counterclockwise around the unit circle, then sine theta gives you your y-coordinate, and cosine theta gives you your x-coordinate. Similarly to a circle, an ellipse is defined using distances from points. In the ellipse's case, it uses 2 points, each of which is called a focal point or a focus, plural being foci. An ellipse is defined as follows. If you choose any point on the ellipse, take the distances from that point to each of the focal points, then add those distances up, you will always get the same number no matter which point you choose. Thus, the ellipse is a generalization of the circle. The circle is simply the special case where the 2 focal points are the same point. An ellipse can also be thought of as a stretched out circle. The equation for an ellipse centered at the origin with a width of 2a and a height of 2b is x squared over a squared plus y squared over b squared equals 1. The farthest points on the ellipse from the center are called the vertices of the ellipse, and the closest points are called the covertices. A line segment from the center to a vertex is called a semi-major axis, and one from the center to a covertex is called a semi-minor axis. The distance c from the center to a focus is called the ellipse's linear eccentricity, and the value e equals c over a is its eccentricity. Like a parabola, an ellipse is also an example of a conic section. You could slice through a cone to get an ellipse. This is true even in the special case of a circle. A hyperbola is a curve consisting of 2 roughly U-shaped pieces, or branches, bending away from each other. It can be defined in various ways, including as a conic section, like the parabola and the ellipse. It can also be defined using 2 focal points, just like the ellipse, only using the absolute difference of the distances, rather than the sum. A hyperbola centered at the origin can be given the following equations. X squared over a squared minus y squared over b squared equals 1. Y squared over a squared minus x squared over b squared equals 1. This is similar to the equation for the ellipse, but with subtraction instead of addition. If x is in the first term, then the hyperbola opens sideways. If y is in the first term, the hyperbola opens up and down. The 2 points of the hyperbola closest to its center are called its vertices. The line segment between these vertices is called the transverse axis. The hyperbola has two asymptotes, where an asymptote is a line that you get closer and closer to as you approach infinity. The unit hyperbola is the hyperbola given by x squared minus y squared equals 1. It is the basis of the hyperbolic functions, hyperbolic sine, sine h, and hyperbolic cosine, cosine h, which are analogous to the ordinary trigonometric functions. If you draw a line segment from the center to a point on the right half of the unit hyperbola, then the signed area bounded by the line segment, the hyperbola, and the x-axis is denoted by a divided by 2. Signed area means that, if the area is below the x-axis, it's counted as negative. The point where your line segment hits the unit circle has coordinates cosine h of a, sine h a. Sine and cosine are two of the basic trigonometric functions. They give the coordinates of a point on the unit circle given a distance theta that it has traveled around. The graphs of sine and cosine look like waves, and just swing up and down between -1 and 1 forever, which reflects the function's cyclical nature. Waves of this form are known as sinusoidal waves. Due to this swinging behavior, they do not have a limit, as their input reaches infinity. The period of the sine function, or the amount of time it takes to complete one cycle, is 2 pi. This is also known as tau, the ratio of a circle's circumference to its radius, meaning the number of times that the radius fits into the circumference, about 6.28. At theta equals 0, sine of theta equals 0. Then, at theta equals 1/4 tau, or 1/4 of the way around the unit circle, sine of theta reaches a maximum value of 1. At theta equals 1/2 tau, halfway around the unit circle, sine of theta returns to 0. At theta equals 3/4 tau, sine theta reaches a minimum of -1, and at theta equals tau, all the way around the unit circle, sine theta is back to 0 again, and the sine function has completed a full cycle. Similarly, the cosine function also has a period of tau. At theta equals 0, cosine of theta equals 1. Theta equals 1/4 tau, cosine of theta equals 0. Theta equals 1/2 tau, cosine theta equals -1. Theta equals 3/4 tau, cosine theta equals 0. And theta equals tau, cosine theta equals 1. An exponential function is a function of the form y equals a to the power of x. This can be used to model either exponential growth or exponential decay, depending on whether a is greater than or less than 1. For a greater than 1, the function grows as its input increases. It approaches 0 on the left and rises toward infinity on the right. Meanwhile, for 0 less than a less than 1, the function actually does the reverse, trending downward from positive infinity on the left and decaying asymptotically towards 0 on the right. This corresponds to the fact that repeatedly multiplying a number bigger than 1 by itself will give you a bigger number, but for a number less than 1, you'll get a smaller number. If you try plugging in a equals 1, you get the function y equals 1 to the power of x, which just reduces to y equals 1, so it doesn't grow or decay in either direction. You can also plug in a equals 0 to get y equals 0 to the power of x. This can be broken up into 3 parts: x greater than 0, x equal to 0, and x less than 0. For x greater than 0, the value of 0 to the power of x is just 0, meaning the graph for positive x is the same as y equals 0. For x less than 0, the expression 0 to the power of x is actually undefined. You can't raise 0 to a negative power. Thus, the graph actually doesn't exist for negative x. As for x equals 0, that would require evaluating 0 to the power of 0. The value of this expression is actually not universally agreed upon. Different people hold it to have different meanings or different justifications. It is conventionally either given the value of 1 or left undefined, so the graph may or may not include the point 0, 1, depending on the convention used. In calculus, the most important exponential function is y equals e to the x power, where e is Euler's number. Y equals e to the x power, also denoted by exponential x, is its own derivative. The rate of change at each point is the same as the value of the function at that point. d dx of e to the x equals e to the x. Due to this, it is also its own antiderivative, so it can be obtained by integrating itself. The integral of negative infinity to x of e to the t power dt equals e to the x power. In terms of the graph of the function, this means that any given point on the graph, the height above the x-axis, the slope of the tangent line, and the area under the curve from negative infinity to that point are the exact same value. A logarithm, denoted by log, is an inverse function to an exponential function. Essentially, for any appropriate a and x, log base a of a to the power of x equals x, where a is called the base of the logarithm. In calculus, similarly to how e to the x power is the most important exponential function, the logarithm with base e is the most important logarithmic function. This logarithm has a special name, the natural logarithm, usually denoted by ln. Other frequently used logarithms are the common logarithm, base 10, and the binary logarithm, base 2, with the latter being common in computer science. The graph of any inverse function can be created by taking the graph of the original function and reflecting it across the line y equals x. If we use the natural logarithm, what we get is a curve that shoots up from negative infinity to the right of x equals 0, crosses the x-axis at x equals 1, and then grows more and more slowly as it goes to the right. However, its growth is unbounded, so it will reach arbitrarily high values if you go far enough to the right. We can also graph the common logarithm, which has a bigger base, so it grows more slowly, and the binary logarithm, which has a smaller base, so it grows faster. You can also use a base between 0 and 1 for the logarithm. This results in a graph that plummets from positive infinity, crosses through the x-axis at x equals 1, and decreases more and more forever. If you replace the base of a logarithm with its reciprocal, this is the effect of flipping the graph across the x-axis. For example, the graph of logarithm base 1/2 of x is just a flipped version of the graph of logarithm base 2 of x. The natural logarithm is important in calculus because its derivative is y equals 1 over x. Correspondingly, by integrating this function, you can get to natural log of x. Natural log x equals the integral of 1 to x of 1 over t dt. This is one possible definition of the natural logarithm. Calculus is the branch of mathematics which involves the study of the continuous rate of change of quantities, particularly in the context of functions and limits. It's a fundamental subject that has numerous applications in various fields, including physics, engineering, economics, and computer science. Calculus is divided into two main branches: differential calculus and integral calculus. Before we begin, we must discuss some major parts of calculus: functions and limits. A function is a mathematical relationship between a set of inputs, the domain, and a set of possible outputs, the range. It is a way of assigning each input exactly one output. The input is called the independent variable, and the output is called the dependent variable. A function is only denoted by the letter f, and the input by the letter x. The application of the function f to the input x is written as f of x, and it is equal to the output of the function for that input. The output is often denoted by y. The equation y equals f of x is read as y is a function of x. In the calculus of the real numbers, we study real functions, functions that take real numbers as inputs and give real numbers as outputs. Functions can be represented in various forms, such as equations, graphs, and tables. For example, f of x equals 2x plus 5 is a function because for every value of x, we get exactly one answer for f of x. Consider another example. F of x equals plus or minus the square root of x. It is not a function because each value of x gives more than one value of f of x. Operations on functions involve combining two or more functions in different ways to make a new function. Here are some common operations on functions. For example, letting f of x equal x squared and g of x equal 2x. Addition. F plus g of x equals f of x plus g of x equals x squared plus 2x. Subtraction. F minus g of x equals f of x minus g of x equals x squared minus 2x. Multiplication. F times g of x equals f of x times g of x equals x squared times 2x. Division. F over g of x equals f of x over g of x equals x squared over 2x equals x over 2, where g of x does not equal 0. Composition of functions. Composition has no analog with arithmetic operations. When two functions are composed, one's output is used as the input of the other. For example, FOG of x equals f of g of x, which equals 2x squared equals 4x squared. GOF of x equals g of f of x equals 2x squared. FOF of x equals f of x equals x squared squared equals x to the fourth power. GOG of x equals g of g of x equals 2 times 2x equals 4x. Functions are a powerful tool that help us understand and analyze complex phenomena across various disciplines. They have numerous applications in math, science, computer science, engineering, economics, etc. Functions in action. Calculating the trajectory of a projectile, modeling population growth and decline, optimizing electronic circuit design, predicting stock prices, modeling the spread of diseases, analyzing and visualizing data, training machine learning models. Limits are a way to study the behavior of the output of a function in response to inputs as they approach some number or go to infinity. In other words, it's the value that a function gets closer and closer to, but may not necessarily reach. Limits are denoted by the symbol lim, and are written as limit x approaching a, f of x equals L, where f of x is the function applied to the variable x, a is the point where the limit is being evaluated, and L is the limit value. Limits help us understand how functions behave, define continuity, derivatives, and integrals, and solve optimization problems. Limits are used in many fields, including physics, engineering, economics, and computer science. Example: evaluate limit of x approaching 0, or x over x. The expression x over x is undefined for x equals 0, since that leads to a division by 0. However, we can plug in values of x that get closer and closer to 0. For example, coming from the positive side, we can plug in 0.01, 0.001, and 0.0001. By doing this, we are having x approach 0 from the positive side. These give us 0.01 over 0.01 equaling 1, 0.001 over 0.001 equaling 1, and 0.0001 over 0.0001 equaling 1. So, for values of x arbitrarily close to 0 from above, x over x equals 1. We can also plug in negative values, like negative 0.01, negative 0.001, and negative 0.0001. These values of x will also give us x over x equals 1. Thus, the limit from the negative side is also 1. Since the limits from above and below match, we can say that limit x approaching 0, x over x equals 1. Derivatives are a fundamental concept in calculus that measure how sensitive a function is to change in its input. The derivative of a function f, denoted by f prime, is another function that measures the rate of change of f at a given input value. For inputs around which f is rapidly increasing, the derivative of f has a high positive value. If f is only slowly increasing, the derivative of f has a small positive value. If f is neither increasing nor decreasing, the derivative is 0, and if f is decreasing, the derivative is negative. Let's say we're trying to find the rate of change of f around the input x. The value of the function at that point is f of x. Now let's change x by a small amount, which we'll call delta x. This takes us to the point x plus delta x, and the function's value at that point is f of x plus delta x. To find the average rate of change of the function over the interval from x to x plus delta x, we'll take the ratio between the change in the value of f and the change in x. Delta f over delta x equals f of x plus delta x minus f of x over delta x. Now we just need to consider what happens for smaller and smaller choices of h. Meaning we have to use a limit. Limit delta x approaching 0, where f of x plus delta x minus f of x over delta x. This is the formal definition of the derivative f prime of x equals limit delta x approaching 0 of f x plus delta x minus f of x over delta x. However, instead of delta x, it's usual to use the letter h. F prime of x equals limit h approaching 0, f of x plus h minus f of x over h. This process of choosing smaller and smaller values of h can be visualized on a graph of the function f. The points x, f of x, and x plus h, f of x plus h can be plotted, and a line can be drawn through them, whose slope represents the average rate of change over that interval. As h approaches 0, this line approaches the tangent line to the graph of the function. So, the derivative of a function has a nice visual representation. It is the slope of the tangent line to the graph of the function at the given input point. Since the derivative is defined using a ratio of the change in f to the change in x, it can be represented with the following notation: d of f over d of x. Here, dx means a tiny difference in x, and df is the resulting tiny difference in f, with the understanding that dx is a quantity approaching 0. df over dx is read as the derivative of f with respect to x, meaning the speed at which f changes as x changes. One simple example of a derivative is velocity. Velocity is the rate at which your position changes over time. This makes it the derivative of position with respect to time. Assuming that forward is the positive direction, going forward very fast means you have a large positive velocity. Going forward slowly means you have a small positive velocity. Not moving means you have a velocity of 0, and going backward means you have a negative velocity. Note that velocity and speed are different things. Velocity is how fast you're going in a particular direction, meaning it has both direction and magnitude. Speed is just the magnitude of velocity with no regard for direction. Constant rule. The derivative of a constant function is 0. Y equals f of x equals c. dy over dx equals 0. Constant multiple rule. The derivative of a constant multiple times a function equals the constant multiple times the derivative of the function. D over dx of cf of x equals c d over dx of f of x. Derivative of power. Power rule. The derivative of x to the power of n is n times x to the power of 1 less than n. Y equals x of n, dy of dx equals nx to the n minus 1 power. For example, if f of x equals x squared, then f prime of x equals 2x to the 2 minus 1 power, equaling 2x. Derivatives of sine and cosine. The derivative of sine is cosine. D over d theta cosine theta equals negative sine theta. Sum rule. The derivative of a sum of functions is equal to the sum of the function's derivatives. D of dx of f of x plus g of x equals d of dx f of x plus d of dx g of x. Similarly, d of dx of f of x minus g of x equals d of dx f of x minus d of dx of g of x. For example, f of x equals 3x squared plus 2x. The sum rule states that the derivative of a sum is the sum of the derivatives. F prime of x equals d 3x squared of dx plus d of 2x of dx. Differentiate. F prime of x equals 6x plus 2. Derivative of product of functions. Product rule. When we have a function h of x that's the product of two functions, f of x and g of x, we can't simply multiply the derivatives to find the derivative of the product. Instead, we need a special rule to handle this situation. That's where the product rule comes in. The product rule states that if we have a function h of x equals f of x times g of x, then the derivative of h of x is h prime of x equals f prime of x times g of x plus f of x times g prime of x. Let's take an example. F of x equals x squared sine of x. Apply product rule. F of x equals x squared d of sine of x over dx plus sine of x dx squared over dx. Differentiate. F prime of x equals x squared cosine of x plus 2x sine x. Derivative of quotient of functions. Quotient rule. When we have a function h of x that's the quotient of two functions, f of x and g of x, we need a special rule to find its derivative. That's where the quotient rule comes in. The quotient rule states that if we have a function, h of x equals f of x over g of x, then the derivative of h of x is h prime of x equals f prime of x times g of x minus f of x times g prime of x over g of x squared. Let's do an example. Find the derivative of f of x equals 2x plus 1 over x plus 2. Apply quotient rule. F prime of x equals quantity x plus 2 times 2 minus quantity 2x plus 1 times 1 over x plus 2 squared. Simplify. F prime of x equals 2x plus 4 minus 2x minus 1 over x plus 2 squared. F prime of x equals 3 over x plus 2 squared. Chain rule. When we have a composite function, meaning a function inside another function, we need a special rule to find its derivative. The chain rule. The chain rule states that if we have a composite function, f of x equals g of h of x, then the derivative of f of x is f prime of x equals g prime of h of x times h prime of x. Remember, it's essential to identify the outer and inner functions and evaluate their derivatives separately. Example. Let's say we want to find the derivative of the function f of x equals sine of x squared. This is a composite function, meaning it's a function inside another function. To find its derivative, we'll use the chain rule. In our example, g of x equals sine of x and h of x equals x squared. So, we'll find the derivatives of g and h separately. G prime of x equals cosine of x. H prime of x equals 2x. Now, we'll apply the chain rule formula. F prime of x equals cosine x squared times 2x. Simplifying our answer, we get f prime of x equals 2x cosine of x squared. Derivatives of trigonometric functions. There are 6 basic trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant. These functions are related to the ratios of the sides of triangles and are used to describe periodic phenomena, such as sound waves, light waves, and circular motion. The derivatives of all 6 functions are as follows. d of d theta sine theta equals cosine of theta. d of d theta cosine theta equals negative sine of theta. d of d theta tangent theta equals secant theta squared. d of d theta cotangent theta equals negative cosecant theta squared. d of d theta secant theta equals secant theta times tangent theta, and d of d theta cosecant theta equals negative cosecant theta times cotangent theta. Real-life applications of derivatives. Derivatives have many real-life applications, such as optimizing functions, finding the maximum and minimum values, determining the rate of change of physical quantities, and analyzing population growth and chemical reactions. Here is an example for this. Let's say you are a manager at a company that produces smartphones. You want to know the rate at which your profit is changing with respect to time. Your profit function is P of t equals 1000t squared minus 500t plus 100, where t is time in months. To find the rate at which your profit is changing, you will find the derivative of P of t. P prime of t equals dp over dt equals. Using the power rule and the sum rule, we get P prime of t equals 2000t minus 500. What does this result mean? It means your profit is increasing at a rate of 2000t minus $500 per month. If we want to know the rate at a specific time, we can plug in that value of t. For example, if we want to know the rate after 5 months, we can plug in t equals 5. P prime of 5 equals 2000 times 5 minus 500 equaling 9,500. So, your profit is increasing at a rate of $9,500 per month after 5 months. Integrals are a fundamental concept in calculus that help us solve a wide range of problems in mathematics, physics, engineering, and other fields. So what are integrals? An integral is a mathematical operation that computes the area under a curve, or the accumulation of a quantity over a given interval. It's like finding the total amount of something, like the area of a rectangle or the volume of a box. Differentiation and integration are inverse operations. We denote an integral with this symbol. For example, integral of f of x with respect to x. This reads the integral of f of x with respect to x, where f of x is the function being integrated, x is the variable of integration, and dx is the differential of the variable. There are 2 main types of integrals: definite integral, indefinite integral. Definite integral has a specific upper and lower bound. It is used to find the area between a curve and the axis over a specific interval. It is denoted as the integral from a to b, f of x with respect to x equals f of b minus f of a. It does not. It is used to find the antiderivative of a function. It is denoted as the integral of f of x with respect to x equals f of x plus c. Techniques for integration. Power rule. The power rule states that if we're integrating x to the power of n, we can simply add 1 to the exponent and divide by the new exponent. Integral x to the nth power with respect to x equals x to the n plus 1th power over n plus 1 plus c. Remember, it only works for powers of x. And don't forget to add the constant of integration. Let's try an example. Integral of x squared with respect to x equals x cubed over 3 plus c. Sum rule. This rule allows us to integrate a sum of functions by integrating each function separately. The sum rule of integration states that integral of f of x plus g of x with respect to x equals integral f of x with respect to x plus integral g of x with respect to x. In other words, the integral of a sum of functions is equal to the sum of their integrals. Similarly, when two functions are being subtracted, the expression will be integral of f of x minus g of x with respect to x equals integral f of x with respect to x minus integral g of x with respect to x. Let's consider an example. Suppose we want to evaluate the integral x squared plus 3x with respect to x. Using the sum rule, we can break this down into two separate integrals. Integral x squared with respect to x plus integral 3x with respect to x. Evaluate integrals equals 1/3 x cubed plus 3 over 2 x squared plus c. Integration by substitution. Integration by substitution is a powerful technique that allows us to simplify complex integrals by substituting a new variable. It's like a change of variables that makes the integral easier to evaluate. As chain rule of derivatives is used to differentiate composite functions, integration by substitution is used to integrate composite functions. The formula for integration by substitution is integral f of g of x times g prime of x with respect to x equals integral f of u with respect to u. Here we substitute u equaling g of x. For example, in the following integral 2x plus 1 cubed with respect to x, we will substitute u equals 2x plus 1. The new integral will be 1/2 the integral u cubed with respect to u equals 1/2 times quantity 1/4 u to the 4th power plus c equals 1/8 u to the 4th power plus c equals 1/8 times quantity 2x plus 1 to the 4th power plus c. Integration by parts. Integration by parts is a powerful technique that allows us to integrate products of functions. Imagine you're dancing with a partner. You're both moving together in harmony, but one of you is leading the way. In integration by parts, one function is the leader, the one being differentiated, and the other function is the follower, the one being integrated. In other words, integration by parts is a delicate balance between differentiating one function and integrating the other, much like the harmony between a leader and follower in a dance. The formula for integration by parts is integral f of x times g prime of x with respect to x equals f of x times g of x minus the integral g of x times f prime of x with respect to x. Or simply, integral u dv equals uv minus integral v du. Remember to choose which function to differentiate and which to integrate, and don't forget to subtract the integral of the product. Integral x squared times sine of x with respect to x. Here, we'll let f of x equal x squared and g of x equal sine of x. Differentiate f of x. F prime of x equals 2x. Integrate g of x. G of x equals negative cosine of x. Apply integration by parts formula. Integral x squared sine of x with respect to x equals f of x times g of x minus integral g of x times f prime of x with respect to x equals x squared times negative cosine of x minus integral negative cosine of x times 2x with respect to x. Simplify and integrate. Equals negative x squared times cosine of x plus 2 times integral x times cosine of x with respect to x equals negative x squared cosine of x plus 2 times the quantity x times sine of x plus cosine of x plus c. Integration by partial fractions. Integration by partial fractions is a technique used to integrate rational functions. It's like breaking down a fraction into smaller pieces that are easier to integrate. The formula for integration by partial fractions is integral f of x over g of x with respect to x equals integral a over g of x with respect to x plus integral b over g of x with respect to x, where the degree of f is less than the degree of g. Let's integrate. Integral 2x plus 1 over x squared plus 3x plus 2 with respect to x. Factor the denominator. X squared plus 3x plus 2 equals quantity x plus 1 times quantity x plus 2. Set up a partial fraction. 2x plus 1 over quantity x plus 1 times quantity x plus 2 equals a over x plus 1 plus b over x plus 2. Solve for a and b. A equals negative 1, b equals 3. Integrate. Integral negative 1 over x plus 1 with respect to x plus integral 3 over x plus 2 with respect to x. Result, negative natural log of the absolute value of x plus 1 plus 3 times the natural log absolute value x plus 2 plus c. Definite integral. A definite integral is a type of integral that has a specific upper and lower bound. It's denoted as integral of a to b times f of x with respect to x equals f of b minus f of a, where a is the lower bound, b is the upper bound, and f of x is the function being integrated. Example. Let's find the definite integral of x squared from 0 to 2. Integral 0 to 2 of x squared with respect to x. To evaluate this integral, we can use the power rule of integration. Integral 0 to 2 x squared with respect to x equals 1/3 x cubed evaluated from 0 to 2. Now we apply the bounds. Equals 1/3 2 cubed minus 1/3 0 cubed equals 8 over 3. Real-life applications of integrals. Integrals have many real-life applications, such as finding the area of a triangle or a circle, calculating the volume of a sphere or a cylinder, determining the work done by a force on an object. For instance, if you have a function that describes the velocity of an object, the integral of that function would give you the distance traveled by the object. Here's a real-life example of integrals. A water tank has a leak at the bottom. The leak is shaped like a circle with a radius of 0.5 meters. Water is flowing out of the leak at a rate of 0.2 meters per second. Find the total amount of water that leaks out of the tank in 5 minutes. Solution. Let's use the concept of integrals to solve this problem. The leak is a circle with a radius of 0.5 meters. Water is flowing out at a rate of 0.2 meters per second. We want to find the total amount of water that leaks out in 5 minutes. Set up the integral. The area of the leak is A equals pi r squared equals pi times 0.5 squared equals 0.25 pi meters squared. The flow rate is 0.2 meters per second. We want to find the total amount of water that leaks out in 5 minutes, which is 300 seconds. 5 minutes times 60 seconds per minute. The integral we need to solve is integral of 0 to 300, 0.2 times 0.25 pi with respect to t. Evaluate the integral equals 15 pi meters cubed. The total amount of water that leaks out of the tank in 5 minutes is approximately 15 pi meters cubed, or approximately 47,120 liters. This is just one example of how integrals can be used to solve practical problems. When describing trigonometric functions, it's necessary to talk about concepts such as radian, sexagesimal degree, and gradian. The radian is the angle made at the center of a circle by an arc equal in length to the radius. The size of the radian remains constant, whatever the size of the circle. 1 radian equals pi over 180, or 57.3 degrees. The angle formed by 2 radii of a circle, measured in n radians, is equal to the length of the arc bounded by the radii divided by the radius. That is, theta equals b over r, where theta is the angle, b is the arc length, and r is the radius. Therefore, the full angle subtending a circle of radius r, measured in radians, is theta of the circumference equals 2 pi r over r equals 2 pi rad. Now, let's talk about sexagesimal degrees. Degrees and radians are two different systems for measuring angles. An angle of 360 degrees is equal to 2 pi radians. An angle of 180 degrees is equal to pi radians. In the following graph, it is possible to appreciate the relationship between sexagesimal degrees and radians, in addition to illustrating the signs of the trigonometric functions in each quadrant. The sexagesimal degree is an angle that describes an arc whose length is the 360th part of the circumference. So why do we use radians in calculus and not sexagesimal degrees? The answer: calculus uses radians instead of degrees because they can simplify formulas, especially when working with arc lengths. For example, if you have the arc length in two different systems, radians, b equals alpha r, sexagesimal degrees, b equals alpha over 360 degrees times 2 pi r. As we can see, it is easier to work with radians, but this is a different case for degrees, where it can also be done, but it is important to recognize that as far as arc length is concerned, radians indicate how many times the length of the radius is inscribed in the perimeter of the circumference. Now, we will talk about a system that is perhaps a little less known. The gradians, or 100th degree, is a measure of plane angles. Alternative to the sexagesimal degree and the radian, the value of a 100th degree is defined as the central angle subtended by an arc, whose length is the 400th part of a circumference. Its symbol is a lowercase g in superscript, placed after the number in question. For example, 12.4574 g. The 100th degree, like the sexagesimal degree, does not belong to the International System of Units. Here is the conversion of common angles. When it comes to converting angles, we will focus on the two most commonly used systems, radians and sexagesimal degrees. To do this, we will use conversion factors, as in the following example. Convert 30 degrees to radians. 30 degrees times quantity pi rad over 180 degrees equals pi over 6 rad. Convert 2 pi over 3 rad to degrees. 2 pi over 3 rad times 180 degrees over pi rad equals 120 degrees. The angle measurement system normally used in calculation, as we have already analyzed, is radians. The measurement in radians in any given angle is its corresponding real number. On the other hand, sexagesimal degrees are not real numbers, because they have 60 as their counting base. The radian is a unit of angle measurement in the International System of Units, whereas in the English system, in its angle measurement system, sexagesimal degrees are used. Knowing the angle measurement systems, we will base the entire following theory with radians to illustrate the trigonometric functions. We will first define what is considered a transcendental function. A transcendental function is a function that does not satisfy a polynomial equation whose coefficients are also polynomials. Unlike algebraic functions, which do satisfy this equation, transcendental functions include trigonometric, logarithmic, and exponential functions. Trigonometric functions. A trigonometric function, also called a circular function, is one that is defined by the application of a trigonometric ratio to the different values of the independent variable, which must be expressed in radians. Trigonometric functions are also mathematical relationships that apply to right angles and are defined as the quotient between two sides of a right triangle. Sine function. F of x equals sine of x. It is a real and odd function whose domain is R, the set of real numbers, and whose range is the closed interval -1, 1, is denoted f of x equals sine x for all x is a real number. It is said to be an odd function because it meets the condition that sine of -x equals negative sine of x for any value of x. The sine function has a period of 2 pi. Its graph is symmetric with respect to the y-axis. In geometry, the sine function represents the relationship between the side opposite an angle and the hypotenuse of a right triangle. The sine function can also be interpreted as the change of the opposite side, y minus coordinate, with respect to the angle. Cosine function. F of x equals cosine of x. The cosine function is an even and continuous function with period 2 pi, whose domain is R, the set of real numbers, and the range is the closed interval -1, 1. Being an even function, it means that cosine of -x equals cosine of x. Its graph is symmetric with respect to the y-axis. The cosine function is a trigonometric function that represents in geometry the relationship between the adjacent side and the hypotenuse of a right triangle. The sine function can also be interpreted as the change of the adjacent side, x minus coordinate, with respect to the angle. Tangent function. F of x equals tangent of x equals sine of x over cosine of x. The tangent is an odd function and is a periodic function of period pi, with intermediations in pi over 2 plus n pi. N is an element of the set of integers z. It is a transcendental function of a real variable. In trigonometry, the tangent of an angle, of a right triangle, is defined as the ratio between the opposite and adjacent sides. The trigonometric functions previously analyzed have reciprocal trigonometric ratios. Cotangent function. Cotangent of x equals 1 over tangent of x. The cotangent, abbreviated as COT, CTA, or COTG, is the reciprocal trigonometric ratio of the tangent, or also its multiplicative inverse. Its graph is... The cotangent, being the reciprocal of the tangent, can be defined as the ratio of the adjacent side to the opposite side to the angle in a right triangle. Its range is all real numbers. Secant function. Secant of x equals 1 over cosine of x. The secant, abbreviated as SEC, is the reciprocal trigonometric ratio of the cosine, or also its multiplicative inverse, graphically. The secant function, being the reciprocal trigonometric ratio of the cosine, represents the relationship between the hypotenuse and the adjacent side of a right triangle. Cosecant function. Cosecant of x equals 1 over sine of x. The cosecant function, abbreviated as CSC or cosec, is the trigonometric reciprocal of the sine function graphically. The cosecant function, being the reciprocal trigonometric ratio of the sine, represents the relationship between the hypotenuse and the opposite side of a right triangle. The following graph shows the compilation of all the previously analyzed trigonometric functions, highlighting the 6 main trigonometric functions. We cannot talk about trigonometric functions without talking about trigonometric identities. Trigonometric identities are equalities that involve trigonometric functions and that are valid for all values of the variables that are defined on both sides of the equality. Basic identities. Pythagorean identities. Sine squared of x plus cosine squared of x equals 1. Tangent squared of x plus 1 equals secant squared of x. 1 plus cotangent squared of x equals cosecant squared of x. Even functions. Odd functions. Through trigonometric functions, important trigonometry theorems such as the sine and cosine are also derived. Sine theorem. A over sine of A equals B over sine of B equals C over sine of Y. Cosine theorem. C squared equals A squared plus B squared minus 2AB cosine gamma. Inverse trigonometric functions. In mathematics, the inverse trigonometric functions, occasionally also called arc functions, are the inverse functions of the trigonometric functions. Specifically, they are the inverses of the sine, cosine, tangent, cosecant, secant, and cotangent functions, and are used to obtain an angle from any of the angular trigonometric ratios. The inverse trigonometric functions are widely used in engineering, navigation, physics, and geometry. Hyperbolic functions. Now we will talk about a concept that is perhaps a little less known: hyperbolic functions. Hyperbolic functions are analogous to trigonometric functions, but are defined using the hyperbola instead of the circle. Hyperbolic functions are combinations of exponential functions that have characteristics similar to trigonometric functions. They are used to describe physical phenomena, such as the speed of waves or the motion of an object in a fluid. They are also useful for describing the shape of a high-tension cable, a collar, or the architecture of some structures. Hyperbolic sine function. The hyperbolic sine is a real function of a real variable x that is designated by sine h of x. It is defined by the following equation. Sine h of x equals e to the power of x minus e to the power of negative x over 2. Hyperbolic cosine function. The hyperbolic cosine is a real function of real variable x, which is designated by cosine h of x, and is defined by the formula cosine h of x equals e to the power of x plus e to the power of negative x over 2. Hyperbolic tangent function. The hyperbolic tangent of a real number x is denoted by tangent h of x and is defined as the quotient between the hyperbolic sine and the hyperbolic cosine of the real number x. Tan h of x equals sine hx over cosine h of x equals e to the power of x minus e to the power of negative x over e to the power of x plus e to the power of negative x. Hyperbolic cosecant function. In trigonometry, the hyperbolic cosecant of a real number x is a hyperbolic function defined as the reciprocal of the hyperbolic sine. X equals 1 over sine h of x equals 2 over e to the power of x minus e to the power of negative x. Hyperbolic secant function. In trigonometry, the hyperbolic secant is a hyperbolic function that assigns to a real number the reciprocal of its hyperbolic cosine. E equals 1 over cosine h of x equals 2 over e to the power of x plus e to the power of negative x. Hyperbolic cotangent function. In trigonometry, the hyperbolic cotangent of a real number x is a hyperbolic function defined as the reciprocal of the hyperbolic tangent. Its equation is cotangent h of x equals cosine h of x over sine h of x equals e to the power of x plus e to the power of negative x over e to the power of x minus e to the power of negative x. Just as in trigonometric functions, hyperbolic functions also present inverse functions. Inverse hyperbolic functions are defined as follows. Of course, like its counterpart, Hyperbolic functions also exhibit identities. Some of these hyperbolic identities are as follows. Finally, to illustrate the relationships between hyperbolic and trigonometric functions, it is necessary to analyze complex trigonometric functions. These functions involve a combination of trigonometry and complex numbers. In the context of complex variables, sine and cosine are defined as follows. From Euler's identity, e to the power of I phi equals cosine of phi plus I sine of phi. The sine and cosine in complex variable are defined as sine of phi equals e to the power of I phi minus e to the power of negative I phi over 2i. Cosine of phi equals e to the power of I phi plus e to the power of negative I phi over 2. The trigonometric functions of complex variables and their relationship with the hyperbolic sine and cosine respectively are sine h of phi equals sine of I phi over I. Cosine h of phi equals cosine of I phi. Conic section. Let's take two hollow cones, one of them an upside-down copy of the other. We'll place them so that their apexes, or tips, touch, forming an hourglass shape. Then let's imagine that each cone extends infinitely away from its apex. What we are left with is an object called a double cone. Now we'll take a plane, which is an infinite flat sheet, and we'll place it in this space. This plane will intersect the double cone at a certain set of points. The set of intersection points is known as a conic section, or conic for short. These were considered by the ancient Greeks. For now, let's say that the plane does not pass through the double cone's vertex. In that case, there are three possible types of conic sections. The first is the ellipse, which can be obtained with a plane whose slope is gentler than that of the cone. A circle can also be considered an ellipse, though it is sometimes considered separately. The second type of conic section is the parabola, a U shape that's formed when the plane has the same slope as one side of the double cone. The third type is the hyperbola, formed by a plane that's steeper than the double cone. It consists of two parts, known as the hyperbola's branches. If we do allow the plane to pass through the vertex, we get a conic known as a degenerate conic. This can be a point, a line, or a pair of lines. The lines in question can be either parallel or intersecting. Every conic section can be described in Cartesian coordinates by a certain equation in terms of x and y. Some simple examples are a parabola described by y equals x squared, a circle described by x squared plus y squared equals 1, and a line described by x equals 0. Now let's take the parabola equation and move everything to the left-hand side, resulting in y minus x squared equals 0. The expression y minus x squared is a polynomial in two variables, and the equation states that this polynomial is equal to 0 if and only if the point xy is a part of the parabola. The set of points composing the parabola is known as the polynomial's zero set. As another example, we can rearrange the circle equation to x squared plus y squared minus 1 equals 0. So the circle consists of the zero set of the polynomial x squared plus y squared minus 1. In general, a curve which is defined as a two-variable polynomial's zero set is called an algebraic curve. Lemniscate of Bernoulli. Let's start by choosing a positive real number, which we'll call c. In the Cartesian plane, draw the 2 points on the x-axis that are each a distance of c from the origin. Each point will be called a focus point, or focus for short, and foci for plural. We'll label these f1 and f2. Now, pick some point P and determine how far it is from each focus. These distances will be called pf1 and pf2 respectively. If pf1 times pf2 is equal to c squared, then we will fill it in. Doing this for all possible points in the plane, we will get a figure 8 shape. This is called the Lemniscate of Bernoulli, named after Swiss mathematician and physicist Daniel Bernoulli. It is an algebraic curve, as it can be represented by this equation. Now let's consider what happens if we let c equals the square root of 2 over 2. The resulting lemniscate is given by this equation, and it passes through the points -1, 0 and 1, 0. If we take the arc length of this lemniscate, the distance along the entire curve, and divide it by its width, we get a number known as the lemniscate constant, about 2.62. This is denoted by a cursive Greek letter pi. It is equal to half the lemniscate's arc length. However, it is worth noting that some mathematicians say that 2 pi, the arc length of the entire lemniscate, is the lemniscate constant instead. For those of you who know that the arc length of the entire unit circle is 2 times regular pi, and that this is sometimes denoted as tau and called the circle constant, this should sound very familiar to you. The Lemniscate of Bernoulli is a special type of Cassini oval. A Cassini oval is a shape defined by two foci, where the product of distances to those foci remains constant for every point on the shape. This is similar to the definition of an ellipse, but with a Cassini oval, the product of the distances is taken, rather than the sum. Every Cassini oval is an algebraic curve, given by this equation. Which of Agnesi? In the Cartesian plane, let's call the origin O, and let's pick some point on the positive y-axis and call it M. We'll draw a circle so that the line segment OM is a diameter of the circle. Then we'll draw the tangent line to the circle at the point M. A tangent line is a line that just barely touches a curve at a single point, serving as an approximation of the curve near that point. Now we can pick any point A on the circle other than O, and we will draw a line passing through both O and A. Since this line touches the circle at two distinct points, it is called a secant line. The aforementioned lines will intersect at a point N. Now we'll draw a line through N that's parallel to OM, and a line through A that's perpendicular to OM. These two lines intersect at a point P, and with that we have a point P on our curve. Repeating this process for every possible choice of A on our circle, we get a curve known as the Which of Agnesi. It is named after Italian mathematician, philosopher, theologian, and humanitarian Maria Gaetana Agnesi. If we call the radius of our circle A, then we can write this equation for the which. Which can be rewritten as this. As this is equivalent to a polynomial equation, the which is an algebraic curve. One case where the which arises is in probability theory. A continuous random variable is a variable with uncountably infinitely many possible values. The probability that such a variable falls within a given interval can be determined using a function called probability density function. One example is the probability density function of the Cauchy distribution. Graphing it gives us the which. Folium of Descartes. Here's a Latin language lesson. The Latin word folium means leaf. That concludes our Latin language lesson. The folium of Descartes is given by the equation x cubed plus y cubed minus 3axy equals 0 for some value a. It is named after French philosopher, scientist, and mathematician René Descartes, who first came up with it in 1638. It is remembered for an event that occurred involving Descartes and another French mathematician, Pierre de Fermat. Descartes wanted to test out Fermat's claim that the latter had discovered a method of finding tangent lines. So Descartes challenged Fermat to do so for any arbitrary point on the folium of Descartes. Let's take up Descartes' challenge ourselves. Luckily today we have the benefit of calculus to help us out. In particular, we must use a technique known as implicit differentiation, which allows us to find the slope of the tangent line to any point on an implicit curve. Let's take our equation from before. Now we take the derivative with respect to x on both sides. The right-hand side simplifies to 0. On the left, remembering that a is a constant, we can apply linearity. Using the power rule, the first term is 3x squared. As for the second term, since we are treating y as a function of x, we will use the power and chain rules. The last term requires the product rule. With all the calculus out of the way, all we need is some algebra to solve for dy dx. Now, for any point x0, y0 on the curve, finding the tangent line requires using point-slope form. With that, we have solved a problem that Descartes could not. However, Fermat could, leaving him the winner of Descartes' challenge.